So first, an announcement. Sorry, I'm not sure it's a good news or bad news. No tutorial today, so I guess this maybe can be seen as a good news, but a tutorial tomorrow instead. Because so it's just that, yeah, I won't have time to cover enough material to do what I want to do, so that's why it's going to be tomorrow, because the last tutorial is really going to use what we are going to see today with Young tableau, but also what we're going to see tomorrow with kind of Algebras classification, and I want you to practice a bit on this kind of topic using the root method and linking symbols. So yeah, it's an important part. So I prefer that you have this material to practice tomorrow during the tutorial. Okay, so today what are we going to do? We're going to do briefly some SU2 recoupling theory, very briefly, because we are just going to mention one coefficient, which are the Clebsh-Gordan coefficient. Then, in fact, SU2 recoupling theory, it's much more bigger. So here, what are these Clebsh-Gordan coefficients? It's also sometimes called up to some normalization factor. It's related to the Wigner 3J symbols, and then, of course, you have all these 6J symbol and 3NJ symbol coming from recoupling theory, which have some interest depending on which subject you're working on. For example, so in quantum gravity, in the spin foam approach, which is a path integral approach for quantum gravity, in 3D, you could see that this kind of objects, so the Clebsh-Gordan coefficient, are connected together to form what we say a 6J symbol, and this is the fundamental amplitude associated to a tetrahedron. So in spin foam models, we see space-time as discrete, and this building block are the tetrahedron, and they are related to all these theories. So this kind of, for example, framework could be useful if you're working in this field of quantum gravity. But I'm not going to spend too much time. I just want to mention just the Clebsh-Gordan coefficient for today, and then we're going to go to see. So here, the idea will be to see how can we use. So yesterday, we built all SU2 irreducible representation. So now how can we use them to build different representation? So here, the idea in this first part will be that indeed, starting with SU2 irreducible representation, then you can take some tensor product and stuff like this and get bigger representation. And it's, in fact, what you are doing. And it's where here you have the Clebsh-Gordan coefficient appearing. And then here, we are going to try to generalize what we have seen here in the case of SUN, and we're going to use this kind of Young, these tools. A useful tool is going to be the Young tableau. So what have we seen yesterday? So yesterday we have seen that irreducible representation of SU2 are characterized by a spin J and then a vector space representation. Vj is going to be the set of all vectors of this form, where now M can take the value from minus J plus J. So here, what is the dimension of this representation? The dimension is 2J plus 1. So as we already mentioned, starting from new representation can be obtained from old one by taking, for example, direct sum. So I'm not going to mention it now, but tensor product also of old representation. And so here, in which situation can you come back with see this Clebsh-Gordan coefficient appearing? Just so you don't have to go to quantum gravity. Just in quantum mechanics, if you want to look at the situation where you want to study a system with two particles already, just that, and your particle have a spin, and J1 and J2, and then you want to study the total angular momentum of this system. Okay? So here, of but as we said, we know everything about this SU2 and this space representation space here. So can we use that? And indeed, we can start with what we know. So here, for any particle, we will know the irreducible representation, and we have this representation space. But now if we want to consider the total system, then this means that we consider the tensor, we need to consider the tensor product of the J1 with the J2. So, and now what is the basis of this space? So a natural basis here will be just to consider the tensor. Here will be to take the tensor product of these two vectors, where here I can denote it like this, depending on all these parameters. So how many vectors do you have here? So here we have 2j1 plus 1 times this other vector. But so this is the most natural basis that we can get, but usually these are not going to represent an irreducible representation of your now system. So let's see if we can consider a second basis, would be more. But this one, you know how to build them from what you know already. And a second basis could be to consider a basis labeled by just a spin and a magnetic number, where, of course, this spin is going to depend on the two spin of your two particles. And how do we define? So it's still a basis of this system, but now of this space. But now how this is characterized. For this, you need to consider the total angular momentum. So the total angular momentum here, operator, is just given by this big J, where you add. So you look at the representation of J on VG1, tensor identity on the second space plus so this is your operator. Okay, so this in fact define what we call sometimes a coproduct. Here it's a commutative coproduct. Then if this is generalized, for example, to the case of quantum groups, then this become non-commutative and you have something much more complicated. But here, so in the case of SU2, you have this simple definition. And so how this second basis is defined, what do you get? You get that the representation on the tensor product of the two space acting on this basis is, by definition, going to give you the M and of course you will have access to the J using the Casimir operator of your total system. And again this, so here, yeah, it's really this representation which is defined this way. So you can look at just the zero component to get this operator here, and now you can compute the norm of your operator, and this is going to give you the value. So this is your Casimir operator for your total system. And so here, what are the allowed value here? So you could show, I'm not going to do it here, that J can take the value from absolute value of the difference of the two J to the sum in this decomposition. And of course, the M can again take the value from minus J. So now we have two bases. So how do go from one to the other? So how do we do this change of bases? This is done using the Clebsh-Gordan, what we call the Clebsh-Gordan coefficient. Okay, and so what do we have? We have that to go from these new bases, this vector can be decomposed on this first, the one I call natural basis here. And then here we need to sum over all this magnetic number, M1 and M2. And then what you get so where here this vector base is here, so it's this tensor product, and this is what we this coefficient now. These coefficients are the Clebsh-Gordan coefficient, and they're really defined as the scalar product between these two vectors. And here is what we call this Clebsh-Gordan. And here, so you have some, these Clebsh-Gordan are going to vanish unless you have this selection rule satisfied. So what are the so it's vanish unless, so of course you want your spin J, the big J, being satisfying, being part of this set. So this means that I want to have this, but then you could also show that it's not it's going to be 0 if this is not an integer, and you also so these two first property come from this. It's just come from the fact that you decompose your tensor product here, and you get this relation. And then you have a third one, and the last condition here, it's just this last condition here comes just from the fact that if you the definition of this operator here, okay, defining this way. So you see that here, if you apply this on the first basis, you get M1 plus M2, and here this gives you M, okay? So you get this new condition. Okay, so these are the technical details, some technical detail about the Clebsh-Gordan coefficient. Then you can really find, at least for SU2, you have a very nice expression in terms of the different J and magnetic number here. And you also have books with table with all the different values, but you can also compute them yourself. And then you also have Clebsh-Gordan coefficient for different groups. It's mostly defined for compact groups, but you also have some definition in the case of of non-compact group. And so here, also what does it mean that we can do? This means that if we want to start with the spin 1/2 representation, okay, of SU2, then it seems that using some tensor product, we could have access to all the other representation. And so this could be shown really precisely that, in fact, if you really want that each irreducible representation of SU2 can be obtained by taking some, usually we then symmetrized everything, but so some symmetrized tensor product of spin 1/2 representation. Okay, so these are really kind of the building block of SU2, and then you can have access to everything else using this, this representation, which is also the fundamental representation for SU2. And so now the idea, what we want to do is really to try to go from what we have learned from SU2 to SUN. And in fact, we are going to keep the same kind of idea that we can start from a small thing, and then using some symmetrization or anti-symmetrization, we can have access to the other irreducible representation of SUN. But of course, here, things are going to be a bit more complicated. So in order to have a kind of pictorial way to be, at least to be able to visualize things, we're going to use this Young tableau. Okay? Okay, so this is a second part where we're going to look at irreducible of the special unitary group. And for that, we're going to use this useful tool, which are the Young which are really going to give us a pictorial way to represent finite dimensional representation of SUN. Okay, so first let's recall that we are going first to study what are tensors in SUN. But so first, what is the definition of this special unitary group? If U is in SUN, what does it mean?
Unitary.
Sorry?
Unitary.
Yeah, so what? Yeah, so this means that, how can you write this in terms of just U? So you get that. Okay, and what else do you need?
The determinant of U is equal to 1.
Yeah, okay. So don't forget this S, the special part, which means that you have a determinant 1. And so maybe you may have already heard, even if you haven't done maybe so much particle physics, some statements such as quarks transform as a fundamental representation of SU3 color group. And so what does it mean here? If we look at what this kind of statement means, this means that, so if we denote the quark or any general state of UN, so we look at the general state of SUN, we could be, as in my could be a quark, and in the case of n is equal to 3, then you have the color SU3 color group, sorry. So the general state, we can represent that denote that as a vector with coefficient. So let me maybe use. And so this means that if it transforms as a fundamental representation of SUN, what does it mean? It means that it satisfies that the transformation can be written here like where U is a unitary matrix. Plus determinant is equal to 1. And here, okay, so this would be a vector or state which transforms under the fundamental representation where we just look at matrices of the same size, okay, because we are in the fundamental representation. But now, so let's introduce more structure here and look if we have a more complicated state given by some tensor, okay? So first, we can define an inner product here. Where we will have so we are in complex number, so use the same notation. And if we want this inner product to remain invariant, so we want inner invariant, okay, the definition, in fact, of this SUN group is that the inner product of Cn is invariant. So we have, which is given by, we want that this transform as and so here we said that this state transforms in the anti-fundamental representation of SUN. Okay, so here this means that transform under the fundamental of SUN. So this is for vector. So now what can we say about tensor and what are tensors? So tensors are going to be those quantities that have the same transformation law as the direct product of vectors. Okay, so if you can define, and so let's just first focus on the simplest example. So let's go to something a bit more complicated than vector. Let's go to rank 2. Tensor. And so, as I said, it's going to transform as the direct product of vector. So you see that it's exactly what we considered before when you have here this total angular momentum. We consider the direct product of this vector. And then the question was how to decompose that as irreducible representation. And this is going to be the same issue that we have now. So, but first, so this is a rank 2 tensor. I'm going to use so 2 indices, and we have the transformation property now, which become so we have 2 indices, so K U J L C K L. And now something important, because in fact to get irreducible representation we are going to use we need to symmetrize or anti-symmetrize thing, as we're going to see. So the first remark here, which is important, is that the permutation between two indices, and in fact, indeed, so this is why also Young tableaux are going to appear. These Young tableaux were first introduced to study really the symmetry group, which is the group of all permutation. Okay, but as an extent now we can. It's also used for some other group like SUN. So the permutation here we are going to see does not change. So this is an important remark, this transformation property. Why is that? Let's compute this. Okay, so if now we look at the permutation of this transform vector here, tensor here, this means we are looking at just this tensor with permuted indices here. But let's write what this is in terms of the transformation, the initial tensor. So this is U I L. You can now permute the indices here. So this is also the same thing as saying that you permute the indices of with LK. And so now, since K and L here are summed, okay, I can change the name. It's just a name here. So I can really say that this is also J, L, U, I, K, P, 1, 2, C. So I change, so K, L. And of course I can just reorder everything. I, K, P, 1, 2. These are just numbers now because it's matrix element. Okay, so I can change it. And so you see that indeed we have this exactly. So on P12 CYJ, I have the same transformation than here. Okay? So what does it mean? That means that we can now use this permutation operator to construct the following symmetric and antisymmetric irreducible, because so for this tensor, the irreducible representation are going to be the symmetric and antisymmetric part. Okay, so we can use P12 to construct so usually we use irreps for irreducible representation. So the antisymmetric part and the symmetric part. And the symmetric part is just going to be 1/2 or on the initial tensor. And so this means that we get the symmetric part, and of course you define quite similarly with a minus now. And here what is interesting is that there is no mix. So that's why also it's representation. So there is no mixing between these two parts, the antisymmetric part and the symmetric part. Under SUN transformation. Okay, so what And this is because, of course, P here does not change the transformation law. So to be more explicit here, this means that indeed you really have that this is going to be and so if you apply your transformation law, you transform individually these two guys, okay? Sorry, what? I guess I mixed the indices here. So ij, we want kl, and here. So now let's look at a more concrete example, taking again SU3 that you're going to see when you're going to do look at the standard model. Or even maybe already in QFT. So n is equal to 3. So what does it mean here? So if we start with this tensor, what are the dimensions here? So we have 3 indices, 3 indices. Okay. And it can be decomposed as a symmetric part, as you see, and its antisymmetric part. So what is the dimension of the symmetric part? How do you say if you have 2 indices, you want to look at the symmetric composition? So do you know what is the formula here? For the symmetric part, it's, so n is equal to 3 now. So these are going to be the number of symmetric, divided by 2. Okay, so how many do you get?
6.
Okay, and antisymmetric, so you know the expression. You get them like this. So how many do you get?
3.
So this is the kind of strange formula that you are going to see when you look at irreducible representation of this kind of groups. So this means that here this is the dimension of the rank 2 tensor, okay, which is reducible, and then it can be decomposed in terms of irreducible. So here it's dim of the rank 2 tensor. This is reducible. And this can be decomposed into irreducible part. So here you have the symmetric. And then here you have the antisymmetric. And you can notice that the antisymmetric coincide with, so the dimension is also the dimension n here, okay? So we are here dealing with, so this is antisymmetric here. So let's try to investigate a bit more this part, so the antisymmetric part, okay, by looking at this combination, because, so we want something why do we look at this combination? So we focus on this antisymmetric part. So let's write it explicitly maybe, otherwise you're going to get lost. So this was just, so let's focus on and everyone agrees that I can have access to the antisymmetric part just looking at this combination where epsilon ijk is a totally antisymmetric, is a Levi-Civita symbol, it's totally antisymmetric. So again, I'm going to choose an 1, 2, 3 is equal to 1. And then you have also 1, 2, 3, 1 is equal to 1, 1, 3, 1, 2 is equal to 1. And then you can permute indices. So 2, 1, 3 will be minus 1. And then you get minus 1 also for 1, 3, 2, and 3 to 1. So do you agree that we have access to the antisymmetric part using this combination? Because so you see that the symmetric part, since this is antisymmetric in JK, if you look at something symmetric here, this is going to be 0, okay? So only here, because of course you can write your tensor as the sum of S and the sum of A, okay? So here, if now you contract your tensor with this epsilon ijk, you end up having only the antisymmetric part, and this also is, so now what is the only index that we have? We only have one index. We can take 3 values, and indeed this is the dimension of the antisymmetric part. Okay, so everything is fine here. And so this is in 3D then. Now we want to find how this is going to transform, okay? And so first we can show that epsilon ijk is invariant under SU3. So how can we show that? So we want to show that as a tensor invariant and to show that, I'm going to use the fact that, so how to introduce this? If I have this expression for, so if I have a matrix, so you're going to understand why I'm introducing that now. So if I have a matrix M, the determinant of M can be expressed using some epsilon. So of course, if the dimension of M is greater than, so what is the formula for any dimension? And then we're going to apply that in 3D. Okay, so in 3, so now if we look at the Levi-Civita symbol for an arbitrary number of indices, and then we can write that the determinant of a matrix M can be written as epsilon I j k. I try to keep the same indices, otherwise I'm going to get lost. So M, and here I have all. So let's start with, and then PQ. Okay. JQ, and then M, and I'm finishing with, let's say, S. And here I need another epsilon. So I need this indices, P, Q, and the last one is S. So this is the expression of the determinant. This gives you the determinant of a matrix which is here n time n matrix, okay? So in the case of, now we can have only 3. If we rewrite this in the case of epsilon ijk, so n is equal to 3, what do we get? And now I'm looking not at any matrix, but I'm going to look at a unitary matrix. So for a unitary matrix, the determinant is going to be 1. So here what I get that epsilon ijk ui uj uk, and then I need some additional indices here, and ml. This is equal, so this is this side of the equation applied for m is equal to u, and we have only in dimension 3. And so this is equal to m, and so nml, sorry, nml, and because here we had the determinant of u in the expression, but this is 1, okay, because we are looking at a unitary matrix. Okay, so here this indeed shows that epsilon ijk is invariant under SU3. And so now, how can we work with this formula? So maybe I need to go I need more space. Oh, good. You've seen the constraint system today. This is good. Okay, so let's start now from this expression and see what we can say about how this antisymmetric part is going to transform. Okay, the transformation. So my starting point now is this expression equal L. Or maybe should I kept epsilon L M N. Okay, so now I can multiply by. So what I want now is try to find how this object is going to transform under SU3 to characterize this. So let's multiply this expression by the inverse. So in this side, the L is not summed. Okay, I cannot, of course. So I can multiply both sides with. So this is also given by the adjoint, okay? And so this then simplify Km U Km is equal to epsilon Lmn times So now we have that the antisymmetric part, so Aij, which in fact can be just written as epsilon ijk. It's not really. I cannot really write an equal sign because indeed I have, this is three-dimensionless, but here I still have two indices where here I have only one. So how this is transforming So what do we get? We know that this is epsilon, by definition, this is epsilon I jk uk L mn. And we have just shown this equation here. So this is also equal to epsilon to the action of this matrix on Okay, nice. So this is what we wanted to get. And if you look at what I wrote here, that this vector here transforms in the anti-fundamental representation of SUN. You see that here, in fact, the antisymmetric part of your tensor is also transforming under the anti-fundamental representation. Okay? So this transform as, and this is so we characterize which representation, irreducible representation, was this. So in fact, this strange equation that you add here, 3 times 3 is equal to 6 plus 3, in fact, should be written even like this. Okay, we're here, which means that so a rank 2 tensor, okay, for SU3, which is not an irreducible representation, can be decomposed into a symmetric part, the irreducible representation, the symmetric irreducible representation, and the anti-symmetric irreducible representation, which transform under the anti-fundamental, and this exactly means that here. Okay? So now, if we want, so you see that this was for a quite simple case. We just look at a rank 2 tensor. So after the vector, it's the easiest thing we can consider. So if we want to consider more complicated object, then it will be quite useful now to introduce this Young tableau. So I'm going to give you what are these Young tableaux, more or less, and tomorrow in the tutorial you will have a part where you're going to try to use them by yourself. Okay? So let's introduce any question before? Okay, so where is... Let's start now with Young tableau. So I recall the Young tableau are going to give you a very nice pictorial way to represent finite dimensional irreducible representation of SUN. Okay, so that's why we're going to introduce them here, but I'm not sure you will see at the end of this lecture exactly what I mean by this sentence now, but hopefully at the end of the tutorial it will be more clear, okay? Because you will need to practice a bit by yourself, because of course it's a bit abstract. So, in terms of the fundamental representation will be represented as this nice just square with this I component, and then we need the operation of symmetrization. Where, in fact, in the literature, you usually don't use really new letter like here. I introduce this S, Ij, but since then you want to be able to generalize this for much bigger tensor. Of course, for each tensor that you are going to symmetrize some indices, you're not going to introduce a new notation each time, okay? So the way we represent that, and it's what you're going to see in the, for example, if you look at the book of general relativity, is using this bracket, okay? So this means that here these two indices have been symmetrized, and in terms of this Young tableau, we get this. And this, of course, is exactly what, to be sure that this is clear, is exactly what I defined, meaning that it's when you implement the permutation on your... Okay, then what is the operation of anti-symmetrization? So again, usually you don't introduce a new notation as soon as you anti-symmetrize two indices, okay? And so the way we say that we have anti-symmetrized the two indices I, J, we use this square bracket now, okay? So you have this curly bracket for symmetrization. This is, sorry, so this now is anti-symmetrization, so it's a vertical. And again, this is exactly what I defined before. And so, for example, if I combine all this, I can give you a bit more a more complicated example here. And I'm going to try to see if you understand what is this object. So here, I, j, k. And so what does it mean here? Of course, I have a tensor with 3 indices, and the first 2 here are symmetrized, and then it's anti-symmetrized with the third one. So where here does this exactly mean? So just to try to see if this more or less is clear, can you take, I don't know, 20 seconds or a bit more if you need to just try to express this in terms of, can you express this object in terms of the Okay, so I need to think about that, and I'm going to try to get more space. Okay, so before going there, what did you... So how many terms do you have? 4. Okay, very good. What is the first? Well, yeah, there is no first or last one. You just have to choose one.
IJK.
Okay, this one is...
And JIK.
JIK, and you add a plus or a minus?
Plus.
Yeah.
And
Okay.
a minus.
Yeah.
KJI.
KJI, and then
Minus KIJ.
KIJ, yeah. No, I'm not agree with. So KJI. How did you get this? JKI, yeah. Thank you. Okay. So this is exactly what this means and what this Young tableau means. Okay, so let's go back now. So what we say, we are going to use Young tableau to find irreps, okay, irreducible representation of SUN. So what are...
Symmetric under.
Yeah.
Yes.
See.
Sorry?
That's not symmetric under IJ.
So I... Okay, so let's from here. So IJ, then it's symmetric. AJ, JK, and
See, which order you do like the symmetrization and anti-symmetrization, it matters which one you do first.
Yeah.
So which way is correct? Because the way you...
Yeah, you mean that here I did... So we do first this one. So here we have this, and then on this one we can find the minus. So minus kji, and then so you're saying that sorry, kji is this one, and then yeah, okay. So you're saying that this term here should be the k ij, and it's what you said, I guess.
Yeah.
Before.
Then I don't understand. So you symmetrize it first?
Yeah, because here it's this. So you read first the row, and then yeah.
Okay.
So yeah, all right. Yes. And here it's a minus. Yeah, the order matter, and it's the operator I wrote here. Okay, thanks. Yeah, so everyone agree now it's...
No, I'm not sure.
Okay, so you first do this one, okay?
Yeah.
So you get, starting from this one, you get this one.
Oh, I see. And then you...
And then you impose that on 1 and 3, 1 and 3. Okay? So you get these two.
Oh, okay, so just...
Yeah? Okay, so let's just give you the property. So, what are the property? It's a Young tableau is going to represent a tensor that is symmetric in the indices in each row. Okay, so it's what we have seen. And anti-symmetric in the indices in each column. Now, we are going to use that, but we need to determine what we call a legal Young tableau, okay? Because legal Young tableau are going to give us the irreducible representation. So, the first rule is that length of rows do not increase from top to bottom. Okay, so what does it mean? That means that this kind of tableau is not valid, for example. Just then the length of do not increase with from left to right. So, and you can add no more than. So if you are in the case of SUN here, of course, so this is the same N boxes in a so in other words, what does it mean? It means that it's always going to look as an inverse staircase, okay? So at the end of each row, has at most as many entries as the previous row, and it's the same for any column. So you will have more something like this. Okay, this kind of drawing is going to be a valid and so I won't have time to do so many applications, but we will do the application during the tutorial tomorrow. But just let me give you how you can compute the dimension of a Young tableau representation. So for each tensor represented by a Young tableau, the number of independent components can be easily counted, but you need to have the recipe. So now we consider that if we consider a tensor represented by Young tableau, what are the number of independent components? And the way you, so you first, so it's just a recipe. Label, so the first here, upper left corner by n. Okay. And then you increase the number if you are going along a row, and you decrease it if you are going along a column, like that. Okay? Then we're going to, so this is the first. Then the second step is to count the sorry, hooks for each box. So hook starts from one box and goes right and down. That is, the hook number of the box is equal here to the number of boxes to the right plus the number of boxes below it, plus 1 for itself. So for example, if we just look at here, so I have 1 on the right, plus 1 down, plus 1 for itself. So here I get 3. But for this box, the count is just, there is nothing on the right, nothing below. So it's just 1. And here I get also nothing below, nothing on the right. So it's just 1 for itself. And then the number of independent components, so this is the kind, is given by this ratio, where the product of the two results here. So you take first the product here and then this product. So here, for example, what you get is n times divided by 3. And so you can check that indeed when n is equal to 3, how many indices do we get? This gives just, so in the case f n is equal to 3, for this specific tensor, we get the number of independent components so what do you get? So 3 times 4 times 2 divided by 3. So at the end, times 4 times 3 times 2 divided by 3. So at the end we get 8. So this is the number of independent components for this tensor here, okay? So, of course, since this is also the dimension of SU3 here, this means that here, in fact, what we are giving to you is the adjoint representation, okay? Because this is also the dimension of SU3. So but you will see that, so I'm not going to give more examples here. We will come back on that during the tutorial, don't worry. I just need, before the end, to give you a last rule, because usually we want to do, as we did at the beginning of the lecture with SU2 representation, we have a tensor product of two representations, and we want to write that as irreducible representation. Okay, and so this is what we call a Clebsh-Gordan decomposition, and we can combine two Young tableaux together and decompose it into irreducible representation, and you get directly the result. And so this is really what makes things nice, is that you can really combine. So here, now it's a kind of Clebsh-Gordan decomposition. And the idea is that you can combine two Young tableaux. So each of the Young tableaux is going to represent a tensor for SUN. And you want to decompose that into irreps, irreducible representation. And so this is now, you also have again a kind of recipe. So I can just give you the recipe if, so let's do simple for the moment. If the second Young tableau is just a box, meaning that in fact you're just dealing with a vector. To give you an idea how things works, and then you can of course generalize this recipe for much more general Young tableau. So here, what you're going to do to decompose into irreps, you're going to attach this single box to the first. So here I didn't give you any assumption on the first Young tableau. It can be as complicated as you want. In all possible way. So here the possible way, since you have only one box, is just going to be the right and on the left and below. So possible way here in right and below. And of course you need to do that. So all possible ways, such as the resulting Young tableau is a legal one. Okay? Meaning he has to satisfy the three properties that I listed there. And so let's just illustrate this. So this, and of course, so this is when you have this second tableau is just one box, okay? Then, of course, if you want to generalize this to a second Young tableau more complicated, then you're going to do the same thing box per box. Okay, you can in fact do that straightforward. But let's just see if we go to this example we started with, meaning, in fact, I told you that the tensor of rank 2 can be really seen as just the tensor product of two vectors, the way it's transforming. So this means that we have combined these two. So this is the example we started with SU3, okay, where we looked at IG, and we decompose it into the irreducible representation, and we found that you get the symmetric part plus the anti-symmetric part, which transform under the anti-fundamental representation. Okay? So can we see that here? Indeed. So this means that now I want to apply this recipe to these two boxes. So the way I can glue them together to get this is very simple because I only have two single boxes. So indeed, the two allowed Young tableaus I'm going to get are exactly this one, which is a symmetric tensor, and this one, which is the anti-symmetric tensor. And now it's quite easy to check against the dimension. If you remember, we started with this dimension here is equal to 6 plus 3. So let's now try to apply this formula I just did here. So again, the first number here are not going to. So here, let's do the dimension to conclude, and then you will do more. I can do just this one, and you will do the other one. So here we need first, at the top, at the numerator, what do we get? We get n is equal to 3, and then the second box, it's time, since it's horizontal one, it's n plus 1, so 3 plus 1. And then divided by here, what are the hooks? So here, how many boxes do I have? I have only 1 on the right and 0 below, plus 1. So here it's going to be 2 times 1. Okay, so it's divided by 2. And so indeed, I get 6. And here, for this one, I would get that I start with 3, but then the box below is going to be n minus 1. So it's 2. And then here, if I do the denominator, what I get, I'm starting with one box below. So here I get 2, 1. So it's also divided by 2. So I get 3. So the counting is, the dimension is correct. Okay? And here, these two vertical boxes represent the anti-fundamental representation of SU3. And this result can be generalized to SUN. Okay, but you will work more with Young tableau in the tutorial, so I think I can stop here.